For question number 5, now we're getting into these pulley systems. And what I was trying to say in the class is that when you have a pulley, it changes the direction, but actually in a lot of ways it doesn't really change the problem. You can think of this as a 40 kilogram mass attached to a 15 kilogram mass being pulled by some kind of a force. This is a one-dimensional problem, and we would just treat it in one dimensions. The fact that this pulley exists means that it changes the direction, and now in some ways, in every way, the 15 kilogram mass becomes the unbalanced force. I don't know if that makes sense to you, but we still solve these problems the way we would do Newton's third law problems, where we either chunk them together, look at the mass of the whole system together, or look at the mass of each individual piece, the 40 and the 15. So I want to try to do that, and if you have questions as we're going through it, really just note those down and ask me about them, because this can be a little bit tricky. So if we treat this like a, well, actually before we start treating it like a system, think about the acceleration of this object. If we let this 15, there's no friction in this example. If we let this frictionless table, yeah, if we let this 15 kilogram block go, what will happen? It will accelerate. It will start to accelerate down. Now, it does not accelerate at 9.8 because it's got the inertia of this 40 kilogram block holding it back. So if there was no rope here and it was just the 15 kilogram, it would accelerate. A would be just G. But because it's actually accelerating the whole mass, it's not accelerating at G, it's accelerating at less. But whatever that acceleration is, it's the same for both the 15 kilogram and the 40 kilogram. So we can still consider this problem as a combination. So 40 plus 15 is 55 kilograms. The trick is to figure out what are the forces acting on this in the direction of the acceleration. So for this 15 kilogram mass, the only unbalanced force is coming from the gravitational force on the 15 kilogram mass. So it's like you're kind of accelerating a fifth. So this is the Fg on the 15 kilogram mass, which is a little bit tricky to think about, but it's the only unbalanced force acting on the system. Okay, Fg on the 15 kilogram mass is just equal to 15 times g times 9.8, right? Which equals, let me see if I can turn this light on without throwing this off too much. 15 times 9.8 is 147. So this is 147 newtons. So you've got 147 Newton force accelerating a 55 kilogram block. So what we're saying here is that we can do our F net equals ma, F net equals the sum of the forces. So F net, well, I think you've got the idea of that by now. So I'm just going to go ma equals the sum of the forces. So the mass we said was 55. We want to find A, and we're saying since there's no friction, there's no other force impeding its motion. And then we would say this sum of the forces is just 147. So A is simply 147 divided by 55. That's 2.7 meters per second squared. Okay, so what I want to say is this. There is a tension force here. There is a tension force here. This has normal, this has gravity. All the other forces are either balanced out or they are internal. When we consider both the masses together, the tension and the strain, you see how it doesn't even factor in? Because it's internal to the 55. So it doesn't even matter. We can just treat this as the whole thing. Now, to explore this with more detail and to unpack what goes on with the tension, we're going to look at question 6. But for question 5, this is really all we had to do.